In the vast, silent expanse of cosmos, a revolution is quietly taking shape, one that harks back to the very origins of human ingenuity. It is a revolution not of gleaming metals and futuristic alloys, but of a material as ancient as our planet itself: wood. The burgeoning field of renewable space engineering is challenging the very foundations of how we explore the final frontier, and at its vanguard is an innovation that is as surprising as it is promising: the wooden satellite. This is not a whimsical flight of fancy, but a serious, science-driven endeavor to address one of the most pressing challenges of our modern space age: the ever-growing cloud of space debris that encumbers Earth's orbit. For decades, we have been launching objects into space with remarkable success, but this progress has come at a cost. With each launch, we have been contributing to a vast and growing junkyard in the sky. This space debris consists of everything from defunct satellites and spent rocket stages to tiny flecks of paint. These objects are hurtling through orbit at astonishing speeds, many in excess of 28,000 kilometers per hour. At such velocities, even a minuscule fragment can have a catastrophic impact. A paint chip, for instance, can strike with the force of an exploding hand grenade, capable of destroying a multi-million-dollar operational satellite. The scale of the problem is staggering. As of early 2025, space surveillance networks are tracking over 36,000 pieces of debris larger than 10 centimeters. Beyond these, it is estimated that there are approximately 1 million objects between 1 and 10 centimeters, and a staggering 130 million objects smaller than 1 centimeter. This orbital congestion poses a direct threat to our active space infrastructure. The 2009 collision between an inactive Russian satellite and an operational Iridium communications satellite serves as a stark reminder of the destructive potential of space debris, creating thousands of new debris fragments. This has led to a growing concern about the Kessler syndrome, a theoretical scenario where the density of objects in low Earth orbit becomes so high that collisions cause a cascade of further collisions, rendering space activities unfeasible for generations. The problem is not confined to orbit. As defunct satellites are deorbited, they burn up upon re-entering Earth's atmosphere. For years, this was considered a clean method of disposal. However, recent research has raised serious concerns. Conventional satellites are predominantly constructed from aluminum. When these materials burn up, they release a fine shower of metallic particles, most notably aluminum oxide, into the upper atmosphere. These particles can linger in the stratosphere for many years. Studies have shown a dramatic increase in these metallic aerosols. Between 2016 and 2022, the amount of aluminum oxides from satellite re-entries increased eightfold. A single 250 kilogram satellite can produce roughly 30 kilograms of aluminum oxide nanoparticles. With planned satellite megaconstellations, as much as 360 metric tons of these particles could be released annually. Scientists worry these particles could trigger chemical reactions that deplete the ozone layer and alter the Earth's thermal balance by reflecting sunlight. In the face of these mounting challenges, a team of researchers in Japan turned to an unlikely material for a solution: wood. The idea, at first glance, seems counterintuitive. How could a material we associate with log cabins withstand the rigors of space? But as a collaboration between Kyoto University and the Sumitomo Forestry Company has shown, wood possesses a surprising array of properties. The LignoSat Spacewood project was born out of a desire for a more sustainable way to explore space. The idea is simple. If satellites could be made from a material that burns up completely and cleanly upon re-entry, we could significantly reduce atmospheric pollution. Wood, being natural and biodegradable, fits this bill perfectly. Unlike their metallic counterparts, wooden satellites would be converted into harmless water vapor and carbon dioxide. But the appeal of wood goes beyond biodegradability. In the vacuum of space, where there is no oxygen or moisture, wood is surprisingly durable. It does not rot or burn in the traditional sense. The concept of using wood in aerospace is not entirely new. The very first aircraft were constructed from wood and fabric, with spruce being a particularly favored material due to its high strength-to-weight ratio. At the forefront of this wooden satellite revolution is LignoSat, a tiny cuboid craft poised to have a monumental impact. Developed by Kyoto University and Sumitomo Forestry, LignoSat is the world's first wooden satellite, measuring just 10 centimeters on each side and weighing approximately 900 grams. Its grand ambition is to prove that wood is a viable material for space. The journey of LignoSat began with rigorous tests. Samples of cherry, birch, and magnolia wood were sent to the International Space Station and exposed to the vacuum and radiation of low Earth orbit for 10 months. The results were remarkable. The wood samples showed no significant signs of cracking, warping, or peeling. Of the three, magnolia, or honoki in Japanese, was selected for the construction of LignoSat. This wood, traditionally used for making sword sheaths, was chosen for its strength and stability. The satellite's wooden panels were assembled using a traditional Japanese woodworking technique called sashimono, which relies on intricate joinery without screws or glue. In November 2024, LignoSat was launched to the ISS and deployed into orbit to begin its 6-month mission. Onboard sensors are meticulously monitoring the wood's performance, measuring its expansion, contraction, and ability to shield electronics from radiation. While Japan's LignoSat has captured attention, it is not the only wooden satellite project. In Finland, a team from Arctic Astronautics and UPM Plywood has been working on its own wooden satellite, the WISA Woodsat. Like LignoSat, it is a 10-centimeter CubeSat, but it's made from birch plywood. To prepare the plywood for space, it is first dried in a thermal vacuum chamber to remove moisture. It is then coated with a very thin layer of aluminum oxide. This coating helps to prevent any remaining outgassing and protects the wood from the erosive effects of atomic oxygen in low Earth orbit. The WISA Woodsat mission is designed to gather extensive data on how the plywood performs, equipped with sensors and 2 cameras, one on a deployable selfie stick to provide a clear view of the satellite's exterior. The prospect of sending wood into space is not without its engineering challenges. One of the primary concerns is outgassing. Wood contains moisture that can be released in a vacuum, contaminating sensitive instruments. Another challenge is the extreme temperature fluctuations, which can cause materials to expand and contract, leading to thermal stress. Radiation is another major concern, as high-energy particles can damage electronic components and degrade materials. Finally, there is the threat of atomic oxygen and micrometeoroids. Despite these challenges, the potential benefits are compelling. The development of wooden satellites is a powerful symbol of a broader shift in thinking within the space industry, a move towards what can be called renewable space engineering. This emerging field is about fundamentally rethinking how we design, build, and operate space missions to be more sustainable. One significant area of innovation is the development of green propellants. For decades, the workhorse of satellite propulsion has been hydrazine, a highly effective but toxic fuel. New, safer propellants are being developed, including hydroxylammonium nitrate-based propellants and even water, which can be electrolyzed in orbit. NASA's Green Propellant Infusion mission successfully demonstrated the viability of one such propellant. Another key pillar is the concept of a circular economy in space. This envisions a future where resources are reused, repaired, and recycled in a closed-loop system. This could involve designing satellites with replaceable components, or developing technologies for in-orbit servicing, assembly, and manufacturing. Instead of deorbiting a defunct satellite, we could one day send a robotic mission to repair it, or even recycle its materials to build new ones in orbit. Beyond wood, researchers are exploring a wide range of other biomaterials. Mycelium, the root-like structure of fungi, is being investigated as a potential building material for habitats on the Moon and Mars. Bamboo, with a strength-to-weight ratio superior to steel, is another promising material. Researchers are even studying spider silk and using bacteria to produce bioplastics. The launch of LignoSat and the ongoing development of WISA Woodsat are harbingers of a new era of space exploration, one defined by a commitment to sustainability. The promise of wooden satellites lies not just in their biodegradability, but in the paradigm shift they represent. The challenges are still significant, but the momentum is building. The vision of a future where we build with wood in space, a future of green propellants and circular economies, is no longer the stuff of science fiction. It is a future that is being actively engineered today. The humble wooden satellite is a powerful symbol of this new direction, a reminder that sometimes the most innovative solutions can be found in the most unexpected of places. It is a testament to the idea that our future in space can be as sustainable as it is ambitious, as green as it is grand.